In order to understand Gibbs-Donnan equilibrium, we have to consider an experimental condition in which two compartments A and B are separated by a semipermeable membrane. Both sides contain the solution KCl but in different concentrations. Side A contain 1 molar, whereas side B contain 1.5 molar. So, potassium and chloride ion will diffuse from side B to side A, so that, at equilibrium both sides contain potassium and chloride ion in a concentration of 1.25 moles. However, the scenario changes when we have an impermeable anion on one side. In such a condition, as shown here, side A contain potassium and chloride ions while side B contain potassium and another impermeable anion. Ions which can diffuse will always diffuse across a semipermeable membrane. Here, diffusion starts with chloride ion moving from side A to B. This leads to, at equilibrium, a final concentration of chloride ion is shown. Now, this initial movement of chloride ion will generate a negative electrical potential in B, leading to a subsequent diffusion of potassium ion from side A to B. Hence, an equimolar potassium ions will have diffused to side B to balance the net electric charge. Now, let us also understand electrical and chemical potentials under the effect of which ions move across a semipermeable membrane. Ions move under the effect of two forces, 1. Electrical potential and 2. Chemical or the concentration potential. When an electric current, that is, a negative charge, is present on one side and it attracts positive ions from the opposite side, we can say that the cation has moved under the effect of electrical potential. However, if the same cation moves because of presence of a concentration gradient, it is under the effect of chemical potential. Effects of electrical and chemical potentials are shown above. On the left-hand side, effect of electrical potential can be seen, in which, an electric current of -30 mV applied to side A, causes further diffusion of potassium ion from side B to A. Whereas, on the right-hand side, we can see the concentration difference of potassium ion generating a chemical potential for potassium ion diffusion from side A to B. Here, it is important to note that apart from giving an electric current, there are other ways of generating an electrical potential. One of them is by presence of an impermeable anion or cation on one side. An excess of impermeable anion on one side will generate an excess of negative charge. This is like using a negative current via a microelectrode on side B, as shown above. The net effect will be to cause diffusion of potassium ions from side A to B. Similarly, such presence of an impermeable anion like protein molecules can also prevent or stop the net diffusion of a cation despite of the latter's chemical potential. In such a scenario, we can say that the electrical and chemical potentials are equal and opposite. Now, resuming our preceding discussion, we saw that potassium ions diffuse to side B due to electrical potential created by initial diffusion of chloride ion. But now, since a chemical potential exists for potassium ion, they tend to diffuse back to side A, down the concentration gradient. However, this does not proceed further much, because it exposes the negative charge on anions present on side B. However, at equilibrium a few potassium ions will have diffused to side A. This charge separation establishes a potential difference between two sides that is positive on side A and negative on side B. Movement of potassium ions and the resultant positive charge on side A attracts chloride ion. However, no significant diffusion occur because the chemical potential for chloride ion does not favor diffusion from side B to side A. A few implications of Gibbs-Donnan equilibrium are, 1. The side containing impermeable anion will have slight excess of cations. Here side B containing impermeable anion or protein has slight excess of potassium ions that tend to diffuse to side A. 2. The product of diffusible cation and anion on both sides is equal. This holds true for any pair of univalent cation and anion.